And so we implemented a different garbage collection algorithm that is truly pause-less, in that we don't need to pause the application threads by introducing what's called a read barrier. Every time you access an object, we can intercept that access and we can say, right, do we need to do anything to make sure that we're safe in terms of marking objects and in terms of relocating objects? By doing that, what we can then do is say, right, we can do garbage collection concurrently with the application threads, and that means you don't see any pauses as a result of the garbage collector doing its work in, whilst the application threads are paused.
Simon Ritter, welcome to Software Engineering Daily.
Hi, thanks for having me on.
Absolutely. So you are the deputy CTO at Azul Systems, and just from looking at your background resume, it seems like you've been around the Java world quite a while. Probably know about as much as there is to know about Java. Azul, Oracle, Sun Microsystems. But for those that don't know, maybe just give us a bit of your background and what you do.
Yes. So as you said, I've kind of been doing Java really right from the very beginning. I joined Sun Microsystems way back in January 1996, which makes me feel really old. I literally joined about the same time that JDK 1.0 came out, and I followed Java all the way through the Sun years, got acquired by Oracle, spent another 5 years at Oracle, and then joined Azul a little bit over 7 years ago. And a lot of the time I've been really kind of focusing on helping people understand what Java is and promoting it and kind of driving adoption of Java through various different ways. And as you say, I've been heavily involved in various aspects of that. So currently I'm on the Java SE expert group for the standardization of Java. I'm also on the OpenJDK vulnerability group in terms of how we address vulnerabilities in Java and updates and so on. And I'm on the JCP executive committee as well. So I've kind of got a good feel for what's going on in the Java world.
Yeah, absolutely. I'm sure you've seen a lot of changes, and I want to save some time at the end just to see, hey, what are you seeing that's new in the Java world? Get you excited. We'll talk about that. But I want to start basic. What is a JVM? Why do I need one?
Right. This is really one of the things that makes Java, the platform, so popular, is the fact that you have the JVM. And I would really describe the JVM as the kind of crown jewels of the Java platform. What it allows you to do is to have a managed runtime environment for your applications. And that has a number of kind of advantages. If you go right back to the beginning of Java, one of the things that you would have seen is the kind of catchphrase, write once, run anywhere. And that was a big thing in the beginning, which was you could take the same Java application, compile it once, and then run it on Intel and Windows or ARM and Linux or wherever you wanted to. You didn't have to recompile, didn't have to change any of your code. And certainly in terms of moving into the cloud, that's actually very beneficial because you don't have to worry about exactly what platform you're going to be deploying on now. And the other thing that the managed runtime environment gives you is it takes away some of the hard work that the developers have to do. You look at languages like C and C++, then you're responsible for allocating memory for where you want to store things. And most importantly, you're responsible for figuring out when you don't need that space anymore and freeing it up and remembering to do that so you don't get memory leaks and things like that. So one of the big things that you get in the JVM is this idea of automated memory management. Space is allocated in the heap by the JVM, and it keeps a track of when you're using objects so that when you finish with them, it can run this thing called the garbage collector and then reclaim that space and make it available for new objects as you create those. So that's kind of one of the really key things. And then from a performance perspective, just the ability to take the code that's being compiled into the bytecodes, the virtual instruction set, and compile that at runtime. So rather than doing it ahead of time with a static compiler, what we do is we do it at runtime. And the big advantage of doing it that way is you can actually, in terms of the JVM, you can actually see exactly what that code is doing. You can profile it, see how it's working. And then when you compile it into native instructions, you can optimize it in the best way for what's actually happening in that code. Versus if you do it ahead of time, you don't know what's going to be happening in the application at any given time, so you have to make certain assumptions, and they may not be as good as when you're doing it at runtime. So those are the kind of the key things, is really that idea of automated memory management, just-in-time compilation versus static compilation.
Very cool. And I want to get into more details about the JVM, but one thing you mentioned is hey, the benefits of Java is sort of write once, run anywhere. We've seen a little bit more of that, like with Docker too. How does sort of Java and Docker interact? Do people run Java on Docker? Do they not really need it since Java's already running in the JVM?
Absolutely. I mean, as you say, Docker takes the idea of platform neutrality to sort of one step further, so that you're saying, okay, let's put everything into this container that I need to run my service typically, or application, and then I can ship that around. I can put it wherever I want to. One of the big benefits of using containerization and things like Docker is that you can also have certain number of resources allocated to a specific container, and that's very good in a cloud environment. You say, okay, I've got 2 vCores, I've got 8 gigabytes of memory, and you know that's what you're actually paying for. In terms of how Java plays in that, it plays very well, because you can put the JVM into the container, and especially now that we've got things since JDK 9 with the introduction of modularity, what that allows us to do is to create a runtime which is tailored specifically to the application that's going to run on that. Whereas before we would have the whole JDK and we'd share that amongst many different applications, that would result in having somewhere in the region of 300, 350 megabytes of Java runtime. Now, by using JLink as a command and then stripping out all the bits you don't need, you can shrink that down. If you had the most basic application, you'd be talking about maybe 30 megabytes of runtime. Obviously, as you start doing things in your service, it'll be a bit bigger than that. But it really does sort of reduce it by an order of magnitude. Put that into your container. It's tailored specifically for your application, and everything works really nicely in that environment. So yes, Java does fit very well into this whole idea of Docker containers and so on.
Very cool. Okay, so back to JVMs. Like, what are my options for choosing a JVM if I need to choose one? What are my options there?
Right. So I guess the primary thing that most people look at is OpenJDK. OpenJDK was the project that was created back in, 2006, I think it was, by Sun Microsystems, when they decided to open source Java. Most people will look at that and they'll say, oh, okay, that's the reference implementation for the Java SE standard, so that's the one we're going to use, whether it's the Oracle implementation, which people have used a lot in the past, or from a now much wider variety of providers of OpenJDK distributions. This is certainly something we've seen over the last few years with Oracle changing their licensing terms. There has been a real sort of expanding of the number of that distributions are available. So you've got ones from Azure, obviously. You've got ones from Amazon for running on AWS called Ritter. Even Microsoft have their own JDK distribution, which, as somebody who was involved in Java right at the very beginning and all the sort of shenanigans that went on with Microsoft then, it's quite funny to see them kind of come full circle and go back to creating an open JDK distribution. In terms of alternatives to that, there's really two things you could look at. One is IBM. They have their J9 implementation. The idea behind that was a complete clean room implementation of the specification. They didn't look at OpenJDK. They didn't use any of the source code. They went off completely, did it from scratch. That's still obviously used a lot for IBM software. If you're running things like WebSphere, then you'll be running IBM J9. They did open source it. That's one option. The other option is what we do at Azure, where we take OpenJDK as a starting point, but then we make some significant changes in terms of the way that the JVM works. And that's what we call Platform Prime. So it's based on OpenJDK, fully conformant with the standard. So we run all of the TCK tests, pass everything to make sure that it is a drop-in replacement for OpenJDK. Don't have to change any of your code, don't have to compile any of your code, and you can just use that and get different performance characteristics from that.
Gotcha. And you mentioned sort of the standards and the TCK tests and different things like that. Is that something where sort of every implementation complies to that, or is it more like the sort of SQL standard where it's like, hey, we kind of comply, but maybe there'll be like tweaks here and there that don't comply? Or how well does everything fit that standard?
I'd have to say everything fits that standard very, very well. It's one of the nice things about the Java platform is that we have managed to maintain that sort of compatibility and standardization. Sun started the Java community process as a way of having an open standard for Java. We have all of these what are called Java specification requests, or JSRs. and each version of Java has that specification. So there's a very clear definition of what's in the language syntax, what the JVM has to do from a functional point of view, just not how it does it, and then the core class libraries that are always available for your application code. By using the TCK, and literally everybody, there's probably a couple of exceptions in terms of distributions who don't pass the TCK, but almost everybody does pass the TCK. It gives you that level of confidence that if you're moving from one TCK-tested JDK to another TCK-tested one, your application is going to go run in exactly the same way from a functional point of view. Different performance characteristics maybe, but the way the code actually works will be identical.
Yeah, very nice. It even makes me think back to like Python when I did more of that. There were like different sort of Python implementations. And I feel like there were some, slight things you couldn't do in one or the other. And so that's pretty nice that it mostly works there. I want to talk a little bit more about just like what Platform Prime is doing, but you mentioned sort of Oracle subscription changes, billing model, and I've heard a lot of consternation, I would say, in the Java industry about Oracle new billing model stuff. I don't know how much you want to get into that, but can you tell me about like what Oracle's new billing model is, and how do you think that's going to affect the community, maybe OpenJDK, different things like that?
Yeah, sure. So, I mean, as I mentioned, Oracle changed the licensing that they use, and this is something they've done a couple of times now. When Oracle took over Sun Microsystems, they continue using pretty much the same license that they had from Sun, which was what they then called the Oracle Binary Code License. And that effectively meant you could use the Oracle JDK freely wherever you wanted to, unless it was in embedded systems or on mobile phones. The kind of history behind that was the one place where Sun was making money from Java, so they wanted to force people to license it separately for those types of environments. But for desktops, laptops, server-side applications, you could use the Sun and then Oracle JDK completely freely. There was no problem with that. Then when JDK 9 came out, a little bit after that, Oracle decided that they changed the license and they would impose more restrictions in terms of where you could use it for free. And literally, if you were running Java in a commercial environment, in a server, web server, something like that, then you would need to purchase a Java SE subscription. They've then introduced yet another license for JDK 17, which is called the no-fee terms and conditions, which sounds like it could be free, but it's a little bit, you have to be very careful about the licensing there. And it's only for 3 years anyway. But what they've done most recently is not change the licensing again, but they have changed the way that they calculate the cost of the Java SE subscription. It used to be that you would look at all the machines you were running Java on, you count how many cores you've got in the processors. There was a little bit of complexity in terms of using core multipliers, which meant you had to multiply by a certain factor depending on how fast your processor was and things like that. But it was really based on the number of machines you had and the number of processors, which was pretty logical. But what they've done now is they've said, well, we're going to make it much simpler. All we're going to do now is charge you based on the number of employees that you have in your company. And that's full-time employees, part-time employees, contractors, and so on. And sure, if you're in an IT organization, that's not too bad because most of your people are going to be using Java. But if you're in a company where you've got lots of people doing manufacturing, lots of people doing deliveries or whatever, then to say that you're going to have to pay everybody as using Java, even though you may only have like 5% of your employees using Java, it's quite a shift in terms of the way people are being billed for the use of the Oracle JDK.
Yeah. I mean, you think of just like the company that comes to mind would be Amazon, or Walmart that have a ton of retail and warehouse employees, but not sort of using Java directly, like their sort of technical staff.
Exactly. Yes.
Yeah. Okay. When they were building sort of more on a processor per core basis, were there weird architectural shenanigans to make that bill lower, or was it just sort of not worth the hassle of some of that stuff?
I don't think it was worth the hassle because most people would just look at it as like, okay, what do we need to do to run our applications? And they were more concerned about thinking, okay, we need this number of processors. We'll choose the latest Intel architecture, or we'll choose, like the previous generation of architecture or whatever. And that's where that multiplier came in to determine, what percentage you had to increase the value by for the processes you were using. But most people would focus just on how do I deliver the services that I need to, and then work out the cost from that.
Yeah. Okay. So let's talk about Azure Platform Prime. Tell me about Prime and what it does and why people are choosing to use that over OpenJDK, over Oracle, things like that.
Yeah. So as I said, the great thing about the JVM is you've got this managed runtime environment, garbage collection, just-in-time compilation, and so on. And what we did originally was we looked at the way that the systems work and said, is there a way that we can improve things? One of the big issues that people have always had in the early days of Java, and really, up to now, is the whole idea of garbage collection pauses. It was something that Java was famous for very much at the beginning, and even now people are still trying to eliminate this problem from their application code. It really comes down to the fact that for most algorithms that do garbage collection, in order to do it safely, meaning you're not going to corrupt any of your data or miss things that are being used, you have to pause the application threads whilst you do the work of the garbage collector. And that's obviously, if you're marking to figure out which objects are still in use, you want to do that without people making changes. Same thing, if you're going to move objects around within the heap to do compaction, you don't want people changing the objects as you copy them because you might lose those changes. So the safest way to do that is to just pause application threads. And that works very well, so long as you don't have too much load on the garbage collector. As you start seeing an increase in the use of the heap and place more sort of stress on it, what you'll see is more and more garbage collection pauses because the garbage collection has to kick in more frequently, and you can go from having maybe a few milliseconds of garbage collection pause that can extend out into seconds of GC pause. The longest GC pause I ever came across was one customer who had a GC pause of 1.5 days, which was just like an insane kind of thing to have. And I remember saying to them, well, why don't you just, restart the application? It's got to be quicker. And they said, no, it isn't, because the time it takes to load the data to start the application is actually longer than doing a garbage collection pause. But
can I get some details? Like, how big was the heap for that with the 1.5-day pause?
So that was like terabytes. That was literally tens of terabytes of heap space, and they had a very complex environment, which did result in this incredibly long garbage collection pause. And I remember saying to them, well, how do you even know after like an hour that it's still doing anything? Yeah. Don't you just assume it's crashed? And they said, no, we've got instrumentation. We can see it's still doing the garbage collection, and we know that it will finish after 1.5 days.
And did they have control over like when that garbage collection ran, given that it's 1.5 days? Like, could they run it in certain
No, and that's a very important part about how garbage collection works. Is non-deterministic. You can't predict when it's going to happen. It really depends entirely on how much object allocation you do, how quickly you use the objects and release the links to them, and so on. And this is what we did. We said, okay, well, we looked at that, and this is one of the biggest problems that people see with Java. What we then did was say, okay, how can we take a different approach to that? And so we implemented a different garbage collection algorithm that is truly pause-less, in that we don't need to pause the application threads by introducing what's called a read barrier. Every time you access an object, we can intercept that access, and we can say, right, do we need to do anything to make sure that we're safe in terms of marking objects and in terms of relocating objects? By doing that, what we can then do is say, right, we can do garbage collection concurrently with the application threads, and that means you don't see any pauses as a result of the garbage collector doing its work whilst the application threads are paused. I mean, other algorithms have taken sort of similar approach and tried to do similar things. So the algorithm that gets used a lot in Hotspot, the OpenJDK, is called G1. That does a good job, but at certain points it will actually get to so heavily loaded it'll say, right, I need to stop and do a full compacting garbage collection. So we don't have that. We don't have a fallback situation where we need to do that. And that does allow us to scale up to literally tens of terabytes of heap space. We have customers who do this. When you're doing credit card fraud detection, you need these massive amounts of data, and you need to have it all in memory at the same time. So when this customer had a 1.5-day garbage collection pause and we put Prime on there, suddenly that 1.5 day pause just disappeared, and they're like, that's amazing. So it was really good for them in terms of doing that.
Are
And
there trade-offs to this pauseless one? Like, is that going to use some resources? Like, yeah. What's that?
Well, the answer is yes, because there's no such thing as a free lunch.
Yeah,
if you're going to do the work whilst pausing the application, that work has to go somewhere if you're still running the application. So yes, it is working concurrently. So effectively what we're doing is doing some work at the same time as the application, which then can reduce the throughput of your application, which then brings us to the second thing that we did. Because we said, okay, that works really well now. We've solved the problem of garbage collection. What we now need to do is look at how can we improve the throughput of the applications. And this is where we looked at this just-in-time compilation system. And the way that works is it really happens in three different sort of levels. So you've got the first level, which is just interpreting. You take your bytecode, you convert each bytecode as you see it into native instructions through a template, and then you execute it. That's very inefficient. So the whole idea of hotspot, the name of the JVM, was to identify methods that are getting called very frequently, hotspots of code, and then compile them into native instructions so you don't have to do that interpreting every time. And that happens in two stages. You've got what's called the very originally named C1 JIT compiler, which will compile code very quickly but doesn't apply many optimizations. So you get the code compiled, you can start running it a little bit faster. Then what we do is we profile that code to see how it's actually being used in the application. And then when you get to a second threshold where it really is a hotspot, we pass it to the, again, very originally named C2 JIT compiler. Yeah. That will then take the profiling information and recompile it, optimize it, and generate much more efficient code. But what we said was, well, can we do even better than that? And we looked around and we found that there's a really good open source project called LLVM. It's been around for like 20 years now, and it's all about the back end of a compiler generating heavily optimized code from intermediate representation. And we took that code and we integrated it into the JVM to make it work as a JIT compiler. And then we contributed all that code back to the project because we said, well, open source, we're good open source citizens, we'll put back what we did. What that allows us to do is to optimize the code more efficiently in many situations. We can take advantage of some of the very low-level features that the CPU architecture has more efficiently. As an example of that, modern processors all have this idea of single instruction, multiple data, vector operations. And you get different sort of levels of that. So you've got AVX, AVX2, AVX512, depending on how wide the registers are. What we can do is we can make use of that more efficiently and compile code to use those kind of operations in situations where C2 would not do that. There's lots of things where the compiler just gets a bit confused. As soon as you start doing kind of conditional statements and if statements, most compilers kind of give up and go, oh no, we're not going to bother with that. Whereas Falcon, which is our LLVM-based JIT compiler, will go, oh yeah, I know how to do that, and it will generate much more optimized code. So the advantage of that, as you see, we got the C4 is our algorithm for garbage collection, the continuous concurrent compacting collector. So that, as you said, the trade-off of doing that is that you then reduce throughput. But by using a different JIT compiler, we can improve throughput, and that sort of takes account of the fact that we're now doing GC work at the same time. So the overall effect you get is higher throughput with lower latency. So we solve both of the problems of what's happening with the JVM in the best possible way. So that's kind of like the two main things that we've done internally in the JVM. Yeah. But then we took the next sort of
Hold on a second. I want to talk about some of this compiler stuff because I think this is cool. So LLVM, I've heard of this. This is open source compiler type stuff. Does it work for many different languages? Is that right?
Oh, yes. Okay. I mean, it is all about compiling code from the sort of like, they don't really focus too much on the language itself. You've got the sort of front end of the compiler that takes, Python or C or C++, generates intermediate representation, and then passes that to the back end of the compiler that generates the optimized code. So we've kind of taken that back end part and then integrated it so it takes the same intermediate representation and just generates better code.
Gotcha. Okay. And this is maybe a dumb question because I don't know a lot about compilers, but is LLVM used for both sort of like the just-in-time compiling that Java does, but also like the ahead-of-time compiling that other languages might do?
Yes.
Okay.
Because this project is used by lots and lots of people, and there are lots of companies who contribute to this. People like Intel, NVIDIA, Apple, Microsoft, all of the people who know about these kinds of things are using it to generate the compile code. I mean, even looking at one of our competitors, Oracle have the Graal VM, and Graal VM uses LLVM as part of the way that they handle other languages. So cool. It's a very popular platform.
Okay, cool. I have a question about Graal VM too that I think will come up in the next part. So you're talking about the couple different ways that Platform Prime helps. You mentioned latency with the garbage collection, throughput with the compiler. Third way, you were just about to go into that one before I interrupt.
Yes. So one of the things that you see with the whole idea of JIT compilation is that you start your application and it has to go through this idea of interpreting bytecodes, identifying which methods need to be compiled, using C1 to compile them, profiling them, recompiling them with Falcon or C2. If you start the same application again, it does exactly the same thing. So it has no memory of what happened before. So it goes through the same process of learning which methods to compile, doing all of that work. So we thought, how can we solve that problem? What we now do is we let the application run and warm up so that you've got all your frequently used methods compiled. And you can run it for, an hour. You could run it for a couple of days or a week if you want to. Once you're happy with the level of performance, you then take a profile of the running application. And that stores all the information about what classes you've got loaded, what classes are initialized, the profiling data that was collected whilst the application was running, and even the compiled code for the methods that have been compiled. When you start the application again, rather than starting from scratch, you say, here's the profile from when you were running before. And that way, the JVM immediately knows, right, I'm going to compile all these methods. I've got all the profiling information already available. I've also got copies of the compiled code, so I can sometimes use that rather than having to recompile stuff. And that gives you a much faster warm-up cycle than you would get by just letting it run normally. So you get all the work happen right up front, and then you're at that high level of performance very, very quickly compared to where you would be if you were just running without the profiling.
Very cool. And this is the crack, is that right? CRAC?
No.
Is that different than crack? Okay.
No,
okay.
So this is called Ready Now.
Okay.
So Ready Now is about keeping a copy of all the information about how the JIT compilation system worked so that you can reuse it when you start the application up again. Crack is something that we've been working on, we started developing probably about 18 months ago now, which is another approach that goes even further. It's not quite productized yet, but the idea is that you run your application, you let it warm up, you load all of your information, you've got everything running, and then you can take effectively a snapshot of a running application such that you can then say, right, take the snapshot, store it all in a set of files, and then when you want to start the application up again, you're literally starting from the exact point where you took the snapshot. Okay. And that includes all of the heap, all of the registers, the program counter and everything. You're literally starting exactly as you were before, so that you could be, you could be at the beginning of your application, but you could be running for a week before you take the snapshot and then start again. And that's very, very powerful because it allows you, especially in a sort of microservice environment where you're going to be starting up multiple instances of the same service, then you can actually use this technology to get very, very fast startup. We've done some sort of benchmarking of sample applications, and we did one with Spring Boot, very commonly used framework for enterprise applications. And the time to first transaction was about, I think it was about 3 seconds if we just started up from cold on Spring Boot. Using a crack snapshot, we've really got to change the name of this.
Right.
Crack. Java on crack.
Yeah.
Using a crack snapshot, we reduced that 3 seconds to first transaction to 30 milliseconds. So it's like 2 orders of magnitude faster. and it has some very powerful kind of features that we really are kind of working on. Interestingly enough, Amazon have taken this because we made it an OpenJDK project. They've taken it and they've made it into their, I think they call it SnapStart, which is what they use for their AWS Lambdas, so that they can get their serverless computing. I know we're serverless computing. They can start it up very, very quickly with that. So the problem is that it's not cross-platform yet. Only runs on Linux, so we can't really make it part of the default OpenJDK yet.
Yeah, very cool. Okay, so when would I use ReadyNow? When would I use Crack? How would you sort of distinguish those?
ReadyNow is much more suited to where you've got applications that you're interested in getting fast startup in terms of the overall performance, but you're not looking to store state because you wouldn't have any of the preloaded data and things like that, whereas Crack is where you want a certain state to be available right from the very beginning. So there's two kind of distinct ideas behind that.
Gotcha. With Crack, do you see people doing that more sort of taking that snapshot right after it spins up? So it's mostly that early initialization work, but not a lot of sort of actual data type things, or do you see it sort of all across the spectrum there?
I think it's going to be all across the spectrum. I know that there are quite a lot of people who look at it as, this would be a really good way to be able to be ready to go right from where you sort of, your static void main, and then take a snapshot right there, so you're ready to go. But other people are looking at it as, this would be really cool because we can populate all of our data structures, we can load everything that we need. The downside, of course, is that the more stuff that you store, the bigger your heap is. And in order to take a snapshot, we have to take a snapshot of the whole heap. Yeah. So if you've got an 8 gigabyte heap that's 60% full, you're going to have like 4.5 gigabytes of stuff that you've got to store on disk, and then you've got to load it in when you want to read stuff from it. So again, there are trade-offs between some of the things here. If you're doing more complex stuff, it can be not quite as optimal as if you're doing smaller things. Yeah,
gotcha. What about for ReadyNow? When I take a snapshot, it's not snapshotting the heap, just more the compiled code. How big are those snapshot files?
Oh, those are very small. Because we can do it in two parts. So the information about the methods and the profiling thing, that's literally kilobytes. It's very, very small. It depends to some extent on how much data you store from the code cache, but even then you're really only talking about a few megabytes. So it's not huge amounts of data. We can load that very, very quickly.
Yeah, gotcha. Going back to compilation a little bit, you mentioned sort of there's interpreted, there's C1, there's C2. What sort of, performance impact do you get as you move from interpreted to C1 to C2? How big of a difference is that?
It's huge. Interpreted mode is very, very slow. If you look at the sort of performance graph, anything that's running in interpreted is really slow because you're just not getting any kind of optimization there. C1 is better because now you have a method and it's compiled and it's running native instructions for that method. But the real benefit you get is from being able to use Falcon or C2 to do more heavily optimized code. One of the massive benefits that you get from JIT compilation, and in the analysis that we've done, we find over 50% of the performance improvements of using the secondary compiler, the Falcon compiler, is through what are called speculative optimizations. And that's where you're saying, okay, so we've observed that the code runs in this particular way up until this point. Let's assume that it's going to run for the rest of the time in the same way. And you can do clever things in terms of eliminating code. If you've got like an if statement and you've only ever gone through the true branch, then you assume, okay, well, we're only ever going to go through the true branch in future, and we'll optimize based on that. Now, sometimes you do get situations where the assumption is wrong and you have to throw away the code, and that's called a de-optimization. But one of the things we do with ReadyNow is we record all the de-optimizations that happened, so we can avoid those in future. So it's, again, it's trade-off, but we try to get the best possible kind of way of doing things with that.
Oh man, that's so cool to see those optimizations and see like the hard work that you and your team are doing, and then just how many Java developers get a benefit from that, like basically drop in. I think it's so cool, and without having to know about SIMD or optimizations,
Yes.
customizations, like
Yes.
all kinds of stuff. Yeah.
Exactly. It's kind of taking that level of experience and applying it so that everybody can benefit from it without having to learn about vector operations and so on.
Yeah. Yeah, cool.
There is one other thing that we've done, which is sort of related to that in terms of the JIT compilation, which is where we've said, okay, this idea that the JVM doesn't have any memory of what happened before. We can solve that by using Ready Now. We can solve it by using Crack. But if you're in a cloud environment, what we're seeing is that you have the idea of the microservice architecture where you've got lots of services working together. Now, they're sort of like highly cohesive in terms of the way they work together, but the JVMs underneath don't know anything about each other. What we've said there is like, okay, what can we do to improve that? And the obvious thing is to say, let's take the JIT compilation and take that out of the JVM and turn it into a centralized service in the cloud. And that way, if you've got multiple instances of the same service starting up, first one starts up, it needs to compile certain methods. It sends those to the centralized service. They get compiled. They get passed back. Fine. The next time you start up the same service, when you request the method to be compiled from the centralized service, it doesn't have to compile it because it's already got it. So we're providing a memory through a cache to all of these services. And we can even tailor that in terms of the way that you can have the same method with a different set of profiling information. And that provides like a fingerprint so that the centralized service, what we call the cloud native compiler, will then be able to return the optimized code for that based on the profiling information rather than just the method. And we're going to take that even one step further because we're sort of looking at the idea of, right, so we're running this centralized service. You pass a method to us to be compiled with the profiling. We compile it, we optimize it, pass it back. But then since we've got nothing else to do at that time, we'll start looking at the same method and exploring some other optimizations that would take longer to do, generate some even more heavily optimized code, and then the next time somebody asks for that, we give back even better code, or we can even preempt that and say, oh, I've got a better version for that for you. Why don't you use that one instead? There's lots of interesting things we can do with that.
That is so cool. Yeah, I talked with your coworker, John Ceccarelli, about Cloud Native Compiler. I think it was so cool. Yeah, if people want to go look at that episode is a few months back, but like, yeah, I think it's so cool what's possible there in terms of optimization work. Very cool. Love that. You mentioned GraalVM a little bit ago. I want to talk about that. What is GraalVM? How is that sort of a different approach to some of these problems, I think, around slow start specifically? Like, What's that doing?
Yeah, so GraalVM actually started as a research project way back in the Sun Microsystem days, because I remember from when I was there what they were doing there. The idea behind GraalVM, it's really around multiple different languages. So you can run Java on GraalVM, but you can just as easily run things like C or C++ or Go, all sorts of different languages. But from the Java perspective, the thing that most people are looking at GraalVM from in terms of improving performance is what are called native images. So this is the idea that rather than having a JVM which runs your bytecodes in interpreted mode, then does the JIT compilation whilst the application is running, you say, let's avoid all of that problem and let's compile our code before we start running it into native instructions. So you move away from the idea of write once, run anywhere, platform neutrality, and you say, okay, I know I'm going to be running on an Intel processor, I know I'm going to be running on Linux, let's just compile it for that environment and generate a native image. That way you get a much smaller image because you're only compiling in the code you need, and then you also get very, very fast startup because there is no warm-up. It's instantly at full speed for the application. So this is very good if you're doing things like serverless computing. So very short-lived, ephemeral kind of services work very well with that. The problem is that if you run longer-running services, the performance you'll get, because you're compiling the code ahead of time, is not typically going to be as good as you get with JIT compilation. Because of the fact that you're looking at the running system, you can use these speculative optimizations to improve the efficiency of the optimized code. So you'll see like Graal will give you a certain level of performance, but once you've warmed up your application, you'll see a high level of performance typically not every time, but typically with using JIT compilation. Now, GraalVM will then say, oh, well, we have profile guided optimization. The idea being that you compile your application, you run it, and then you profile it while it's running, and then you take the profile and you feed it back into the compiler and recompile the code. But it still doesn't give you the same level of optimization because you're still doing it statically. And by having the totally dynamic nature that you get with JIT compilation, it is much more flexible. The other drawbacks, if you like, for the GraalVM native image is that you're in a closed environment. There's dynamic class loading you can't do at runtime. Bytecode generation you can't do at runtime. Reflection needs to all be declared ahead of time. So it's possible, but it's a bit more complicated when you do it with GraalVM. Yeah. So there are some limitations in that respect.
For those things, dynamic class loading, reflection, things like that, is that, does that cut out 80% of Java, are most Java applications doing that to the point where it'd be really hard to run on Graal, or how big an issue is that?
I wouldn't say all, but if you look at popular frameworks, if you look at things like Spring, if you look at, Micronaut, Quarkus, things like that, they all use dynamic class loading. They all use reflection. They have adapted so that you can use Spring, you can use Quarkus with GraalVM. There is no problem with that, but it does have extra work involved, and there's a little bit more overhead in terms of that.
Gotcha. And let's say, a day down the road, once I have my Graal version running, I have my normal JVM, running, Azul running. What's sort of the performance? How big of a performance difference is that? I know it's hard to say, but
it's difficult to say. Yeah. If I was to sort of just make a sort of blanket statement, and I'm sure that there'll be a lot of people who go, oh no, that's wrong. Yeah. I'd say somewhere between 20 and 30% is the difference that you'll see.
Yeah. Okay. Sounds good. So if you really need that quick startup time, and you don't have some of those features, reflection, things like that, Graal can work, but you're going to be sort of trading off that top end performance and some of the flexibility of the Java language. Okay. Cool. I like all that stuff. Azul has been on the cutting edge with ReadyMount, with Crack, all that stuff. And then you've been on the cutting edge, I think, of Java's whole lifetime here. What are you seeing that's exciting to you and new to you coming down the pike?
Yeah, it's interesting to see the way that Java has evolved, especially over the last sort of probably about 5 years, I would say, because we've switched from having 2, 3, even 4 years between major releases of Java, and now we have this time-based release cadence, and we have 2 releases every year. So we've got March and we've got September are new versions of Java, and that has led to a much faster pace of development in terms of the platform. We've seen many more features coming through more quickly. The other thing that's been really good from having that faster release cadence is the whole idea of being able to introduce preview features and incubator modules so that features can be added without being kind of set in stone. And that way people have a chance to have a look at them, provide some feedback, say if things need to be changed. And then once everybody's happy, then they actually set it in stone and make it part of the standard. And that's, I think, a really good thing, because it obviously the developers of the OpenJDK are very smart people. You talk to Brian Gertz and Mark Reinhold, they're very smart people. But there's always going to be situations where people go, but if you did it this way or did it that way, it would be a little bit better. One great example of that was the introduction of switch expressions. And in switch expressions, you could use a new style of syntax for them, or you could use a variation on the old style of syntax. And to do the old style of syntax, you would use the break keyword with a value. And people said, well, yeah, you can do that, and the compiler can resolve it, and it all works very happily. But it's a bit more confusing for developers. So why not use a different word? So they said, okay, we'll take that on board, and they switched from using break to using yield. It's a small change, but it was possible because it wasn't part of the standard. And that, like I said, it is a really good thing, being able to address minor kind of irritations before you make it part of the standard.
Yeah. What does governance of Java look like? Is that a foundation? Like what sort of running the release cycle, the features, all that sort of stuff?
Mm-hmm. So all of that is really primarily done through the OpenJDK, this open source project. Now, clearly in terms of the governance, Oracle are the people because they acquired Sun, they acquired the governance of OpenJDK. So they're people who make the kind of ultimate decisions about certain aspects of that. But it is an open source project, so people are free to provide ideas. As I said, we contributed Crack as an idea. It was made a sub-project within OpenJDK. There are other things like Red Hat's Shenandoah garbage collector. That was another project that was contributed there. So there's lots of ideas coming from outside of just Oracle. But ultimately, they have the sort of the final say in terms of governance. But it's an open source project, and everything kind of works nicely through that. We've seen a lot more shift away from the standardization work happening within the JCP to happening within OpenJDK through these things called JDK enhancement proposals, or JEPs. So a lot of the changes now that happen in Java are done through JEPs. We still have the JCP, we still have the JSRs, because we need that standard with the testing so that we can verify that everybody's got the same implement or the same functional way of doing things. But the governance in terms of ideas and so on, much more comes through OpenJDK and the JEPs.
Very cool. Very cool. Well, Simon, I appreciate you coming on. I always love talking to folks from Azul, because you're on the cutting edge of Java and you know this stuff, and I learn so much every time, even though I don't have a ton of experience with Java. So thanks for coming on and walking through all this stuff with me. If people want to find out more about you or Azul, where should they head?
I think the easiest thing is our website. So azul.com is a nice, easy one to remember. I've got to say, it's always great when I give my email address, because it's at azul.com, and it's not a very long email address. Yeah. And the other thing you can do is on Twitter, for people who are still following Twitter, I'm Speak Java on Twitter, so you can follow me there, and I post things about what's going on in the Java world, as well as a few other things.
Perfect. Simon Ritter, Deputy CTO at Azul Systems. Thank you for coming on.
Thank you very much.